Today we're going to look at the topic of permutations, and this is when you list things and the order matters. So let's look at an example. We've got Homer, Lisa, and Marge Simpson here. How many different ways could I arrange these three people into a line? I'd like you to pause the video and try and work out them all. Well, it very quickly makes sense to move away from the pictures and just use the letters. So we're going to have H, L, M. And the question is, how can we be systematic and know that we've got them all? Well, if we keep Homer on the left, the only other one that we've missed so far is Marge and then Lisa. Notice I can't use the same person twice here, I have to just use them each once. So that gives me 2 when Homer is on the left, and it therefore makes sense that there's going to be 2 when Marge is on the left, because there's nothing special about Homer. So it's going to be Marge, Homer, and Lisa, or Marge, Lisa, and Homer. And then finally, we're going to have 2 for Lisa. It's going to be Lisa, Marge, Homer, or Lisa, Homer, Marge. So we get, for 3 people, 6 ways of doing it. Now what I want you to do is try and work it out for 4 people and try and think about what's going on. Well, actually, there's a little sort of cheat version you can also use to help work out what's going on. We could have just looked at 2 people. So for 2 people, if we just take Homer and Marge, then it's going to be Homer Marge or Marge Homer. So 2 gives 2. And actually, you could even say that 1 gives 1 because there's only one way that I could arrange Homer, for example. So let's build that into the table as well. And actually, this is the number of people, and this is the number of permutations. Well, for 4, I'm not going to list them all, but I'm going to try and argue it in a way that will convince you. So let's say I bring Bart into the fold. Well, I could put Bart at the front of every single one of these to give me 6 with Bart at the front. But surely, if I have Lisa at the front, I would get another 6. If I have Homer at the front, I'd get another 6. And if I have Marge at the front, I'd get another 6. So I kind of, we get towards this idea of just generalizing and making convincing arguments. There must only be 6 for Bart, with Bart at the front. Like, how else can I have Bart at the front if I've convinced myself about the 6 ways of combining 3 people? So the same goes for Lisa, Homer, and Marge. What am I going to get? I'm going to get 24. And what have I done actually? What's going on each time? Like, can you make a prediction for 5, for example? Okay, well for 5, it's 120, and you don't want to start writing that down. But if I introduced, I've forgotten her name. What is her name? Maggie. Why have oh yeah, that's why I've given it an A, because there's already someone called Marge. But Maggie, who I've labelled A, well, if Maggie became the 5th person, then I could put her at the front, but I could put her at the front of all of these ones, but then that would give me 24 possibilities, but then I'd have all the others that could be at the front, and there's going to be 5 lots of 24 possibilities. And what I see going on is that actually I just need to times this by 5, and I just times this one by 4, and I just times this one by 3, and so on. So for n people, it's going to be, well, I can see now it's going to be what this 6 was actually 1 times 2 times 3, and then this 24 was 1 times 2 times 3 times 4. So for n people, I'm going to have 1 times 2 times 3 times all the way up to n. And that is the number of permutations I get when I'm ordering n people or n things in a list. So just to say again, with permutations, the order is important. HLM is the same as LHM. And the answer for n permutations is actually this thing here, which we call n factorial. We give it n little exclamation mark and we call it n factorial. I think I say this below. I've tried to give a visual explanation. I've already done this, but this is when I put Bart at the front. So I put Bart at the front, but actually that gave me 6 possibilities. When I put Lisa at the front, I get another 6. This is just another way of looking at it. And here's the answer then. The number of permutations of n distinct objects is n with an exclamation mark, and we call this n factorial, where n factorial is n, and I've written it the other way around now. You tend to write it like this. Rather than 1 times 2 times 3 up to n, you normally start to n and start with n and work your way down. And this leads to a really interesting result you might not have ever thought about. Okay, if you shuffle a deck of cards and the final way it's been shuffled, like if you were to deal it out, for example, it would almost, it's so close to 1 that you would get a deck that's in a different order than has ever been achieved before. And there are more permutations for a deck of playing cards than have been seconds since the beginning of time as we know it. Why is that? Because the answer is the startlingly big, although easy to write down, 52 factorial. And you can find the factorial button on your calculator. It's just above the x to the -1 button, so it would be shift and then x to the -1. And if you put that in, you get 8 times 10 to the 67. Do you know what? I don't know the number of seconds that the universe existed off the top of my head, but it's much, much smaller than this. It's like orders and orders of magnitude smaller. That number is absolutely massive, which makes it, makes this topic quite interesting. You see how quickly it goes up. And in fact, we can relate it to another function that goes up really quickly, something like 2 to the x. This doubles every time x goes up by 1. But you can see with n factorial, it's not just doubling, it's like doubling, and then it's tripling, and then it's quadrupling. It's off the scale. So once I start getting to 52, I'm not just timesing by 2, I'm timesing by 52. It's just getting so much bigger. Okay, actually, before I move on, here's just a couple of questions then. So let's look at the words. I might do this later on, I've forgotten. So how many different ways of arranging the letters in the word maths to make other words? Now, they might not be words that are in the dictionary, but let's just stick with how many different ways of arranging the 5 letters. Well, it would be 5 factorial, which is actually 120, but I just leave it as 5 factorial maybe. And then what about if I have A, B, C, D, E, F, G? How many different ways of arranging that? Well, that's going to be 7 factorial. Okay, what about the word robot? Well, if you said 5 factorial, actually it's not, because it turns out that for robot there are 2 letters that are the same. So actually, if I was to swap these 2 letters round, it would still look the same, essentially. And that's what we're going to look at in a second. So so far we've looked at permutations of distinct objects. I didn't highlight that when we did say that, but they're all going to be different. Now we're going to look at permutations when some of them are the same. Okay, so let's play around with this. What if the objects aren't distinct, i.e. got some counters, maybe the same color, and you can't distinguish between them? Well, let's go with, obviously there aren't 2 Lisa Simpsons, but we can still use this idea to help us. How many different ways are there of rearranging H, L, L, remembering now that L's are the same? I want you to play around with this, maybe try some other ones as well, with 4, with some repeated, or even 5. Okay, so for HLL, remember I can't swap their L's around now, so actually that's it. So if I put one of the L's first, I might then put H second and L third, or if I put the L first, I might put L second and H third, but actually that's it. So when I've got 2 things the same, I've got 3 things, there's only 3 ways of doing it. What if I have another Homer, for example? H, L, L, H. Right, now I can look at maybe moving the H around. It's a bit harder to be systematic, I think. I'm just going to fix a H at the front and then move them around. Whoops, I did that wrong because I've just introduced another H. Okay, so that's possible. So I'm going to get the 3 that I had here, aren't I? So I'm going to get also L, H, L. And I think that's going to be it. If I fix a H at the front, there's only going to be these 3 ways of moving the others around. But if I put L at the front, what's going to happen then? I'm going to get H, H, L, or H, L, H, or L, L, H, H. And I think I'm there again, because again, I've kind of fixed something here, and I'm back to having 3 ways of permutating these objects. So it's going to be 6. So I've got 4 objects, 2, it's hard to write notation for this, but 2 are the same and then another 2 are the same. I actually get 6 different things. If I have 3 objects and 2 are the same, then I ended up with 3. So I suppose the question is, like, how can I generalize this? And it's up to you if you want to play around with it more. Otherwise, I'm gonna kind of give you an argument for what's going on, because it's going to lead to quite a nice result. So let's say I've got 4 objects now, and 2 of them are the same, but I've labeled one of them temporarily as 1 and the other one as 2. Then I know from before I get 4 factorial permutations. But I'm going to need to cancel a load out now. I can imagine, like, this one here is the same as this one, so I cancel that out. And then what other ones can I cancel? I've not actually listed them very carefully here, but I can see that, I've got, so I need the 2 and the 1 that I'm going to cancel with that. So this is going to cancel, so that one's going to cancel. But actually, to summarize, essentially every arrangement comes in a pair, and I can cross out half of them, because the 2 pink objects can be arranged in two ways. In this case, I've written 2 factorial, and the answer for the number of permutations is going to be 4 factorial divided by 2. I'm just going to put a little factorial there as well, because you'll see why in a minute. What about 4 objects with 3 that are pink? Now I get 24 permutations, but actually I've got, for every one, like this 1, 2, 3, I end up with this one being repeated, this one being repeated, this one, and this one. I end up with 1, 2, 3, 4, 5 extra ones. That's because I can rearrange the 1, 2, 3 in 6 different ways. So what I have to do is I have to take my 24 factorial and I have to divide it by 6, because I'm not interested in all these repeated ones. Another way of writing that is to say that it's, whoops, that wasn't right, it was 4 factorial over 6. Or I could write it, and check this out, this is why this notation is just so great. It's going to be 4 factorial divided by 3 factorial. So when I have 4 things to permutate, but 3 of them are identical, then there's actually only 4 ways that I can arrange them that are distinct. I suppose if we do A, B, 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 it's more easy to see now. I can move the A to 2nd place, 3rd place, or 4th place. That's it. And then back to this one. We already looked at this and saw it was 6. Well, this time we've got to be even more careful. So there's 2 ways of permutating the 1 and the 2, but there's also 2 ways of permutating this 1 and the 2 that are yellow. So I'm going to have to kind of cross this one out, but then I'd also have to cross this one out and this one out. So I can see I've got this 4 that are kind of the same. So I'm going to have to divide through by 4. Actually, not just divide through by 4. It's going to be 4 factorial divided by 2, and then divide by 2 again, because that kind of takes into account the different coloured objects. So what do you think now? Actually, let me throw this out as a question. Back to robots. How many different ways of permutating robots? Well, it's going to be 5 factorial, but then I need to divide through by 2 factorial to take into account the 2 O's that are different. Now, let's work this out. Why not? Why not get into that? You can work these things out without a calculator. So this is going to equal and you can write it like, without working it out, I can write it as 5 times 4 times 3 times 2 divided by 2, but then I can cancel these 2's out. And so I'm just going to be left with 20 times 3, which is 60. Okay, let's do a few more before we look at the general rule. We did robots. What about, I don't know why I'm thinking, I got one. Football. How many different ways of permutating this? Okay, so there are 8 things to permutate. Then I've got to take into account the fact that the O's are repeated and the L's are repeated. So to be honest, this one, when I get to this kind of territory, it's going to be hard to do this without a calculator. Well, it's going to take a bit of time without a calculator. So I'm just going to leave the answer like that. I'm just trying to think of another one. Oh, what about Bobby? How many different ways of permutating the name Bobby? Right, well, this is going to be 5 factorial divided by 3 factorial. And now you can do a really nice simplification because you can write this as 5 times 4 times 3 factorial. And then you see that actually these just cancel very quickly. We get to 20. Finally then, I'm trying to not give this away. Right, if we have n objects where p are identical and then q of the remainder identical and r of the remainder identical and so on, how could we work out the total number of permutations? What do you think? Go for it. Go for what you think the answer is. Well, here it is, okay? It's n factorial, and then you just divide by p factorial, and then q factorial, and then r factorial, and so on. Very nice formula for working out permutations. Okay, with our newfound knowledge, we can answer such amazing questions. How many different ways can the letters in the word mathematics be arranged? Have a go. Well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. And then we need to very carefully look at the ones that are repeated. So we've got 2 M's that are repeated. And then we've got this A and this A repeated. And then some T's repeated. And I think that is it. So that's our answer. I'm not going to work that out in full. What about banana? Banana is an absolutely classic one. So it's going to be 6 factorial divided by 3 factorial because I've got 3 A's. And then I'm going to be dividing by the 2 N's. So I want you to try and simplify this using the method that I gave before. Okay, so that's going to be 6 times 5 times 4 times 3 factorial. This is not the only way you can do it, but it's not, not a bad shout. Then I can see the 3 factorial cancels with the 3 factorial. That 2, I can write it as 6 times 5. I can partially cancel the 4 with the 2, so 6 times 5 times 2. And I'm going to get 60 different ways of writing the letters, using the letters in the word banana. Can you think of any yourselves? This is just a fun activity to play around with, although, it's hard to check. It's hard to actually, I don't want to write down all 60, do I? Okay, I'll give you one more. What about abracadabra? Abracadabra. Okay, again, it's 11 factorial. 1, 2, 3, 4, 5 A's. 1, 2 B's. It's quite easy to miss them. You have to really be careful. Maybe be systematic, right? So have I got any more C's? Have I got any more D's? No. And there we go. Okay, not going to simplify that one. All right. We're not going to quite stop there. We're going to just look at a few more challenging questions because sometimes it's just little, extra little things you can add to this, and it's quite fun, I think. So why not? So if a number, and try these. I'm going to go through them, but pause and try them in advance. So if a number plate has to begin with 3 letters ABC in any order with no repetitions and end with 478 in any order with no repetitions, how many different number plates are there? Well, one such number plate would be ABC 478. But note that I always have to have the 3 letters at the front. I can't make it 478 ABC. So actually it's not a 6 factorial question. The answer is in fact going to be 3 factorial because there's 3 factorial ways of arranging this ABC, but it's 3 factorial ways just for 478. But then there's also 3 factorial ways of arranging 478 for every single one of these. And what do we do to deal with that? We actually will multiply them together. I just want to explain that once again. So let's say I've got a 478 here. Well, I'm going to have 3 factorial ways of arranging ABC. But let's say I then change it to 487. I'm going to have another 3 factorial ways. Well, what about 784? Another 3 factorial ways. And in total, it's going to be 3 factorial lots of 3 factorial, which in this case is 36. And then we've got some great questions like this. If the letters in the word minimum are arranged at random, what's the probability that the arrangement begins with MMM? Just trying to, I seem to have lost a few questions at the bottom of the page, so just let me get these back. Okay, I think that's it. All right, well for this one, I've got to think about this carefully. So I'm going to look at the total number of ways that this could be arranged. We've got 1, 2, 3, 4, 5, 6, 7 factorial, but then I need to divide by 3 factorial. And then I've got 2 i's, so I'm going to divide by 2 factorial. And then I've got n and u, that's okay. So that is the total number of ways. We'll worry about that in a minute. What happens if I have to put MMM at the start? Okay, so I'm now kind of fixed with that, and I'm going to be left with I, N, I, U. Okay, these are fixed, so actually the only ones I can move around, because I don't care what happens if I move these around, it'll be the same. The only ones I can move around are the I, N, I, U, and there's going to be 4 factorial ways of doing this, but then I divide by 2 factorial. Okay, and then finally, the probability is going to be this divided by this. So do you know what? I just fancy doing it without a calculator. So this is going to become 4 times 3 times 2 over 2. So it's just going to be 12. There's going to be 12 ways of arranging the minimum with the 3 m's at the front. This is going to be a bit trickier. It's going to be 7 times 6 times 5 times 4 times 3 factorial over 3 factorial, 2 factorial. Cancel out the 3 factorials. Cancel out that 2 factorial with this partially. This is not looking too bad actually now because I've got 42 times 10, so it's going to be 420. And so finally, the answer is going to be 12 over 420, which I could simplify, and maybe I did in my answer here. Let me just have a look. Oh, I've written it like that. Oh, that was an answer from before. But yeah, that is the answer, which I could simplify 1 to 2. And then finally, this is a good sneaky question. 10 pupils are placed at random in a line. What's the probability that the 2 youngest are separated? Okay, so we've got to imagine here that I've got some people A, B, C, D, E, F, G, H, and I've got the 2 youngest, Y1, in y2, but they are all different, in fact. Well, how many ways in total of arranging them? It's going to be 10 factorial ways. How many ways of arranging them so that they're separated? Well, here's the great bit to this question. So this is total. And actually, I'm not going to work out all the different ways they're going to be separated because that's going to be really horrible. I'm going to have to like consider all the different like y1s where I could put. What I'm going to do instead is look at the ways where they're together. So if they're next to each other, they're like this. They're like trapped together. And actually, now I've got 9 factorial ways of arranging this because I'm just like moving these two around together. Except I've got these two as it is, but I could have instead y2 times y1. So in fact, there are 9 factorial times 2 ways of keeping them together. And finally then, for separated, it's going to be the total number of ways minus the number of ways when they're together that gives me the number of ways that they're separated. And if I wanted to work out the probability that they're separated, I would then just divide this by 10 factorial. Wow, what a question, but using the idea of permutations, but then just like these extra little things, these extra little tips and tricks you can add to it, you can answer lots of interesting questions on permutations. I'm hoping you like this right now. Well done.